Hello, everyone. Welcome to today's GPDIS 2020 virtual session. As a quick reminder, this session is being recorded, and I will ask that all questions throughout today's session be submitted through the chat window to all participants or all attendees. My name is Danielle Pirelli. I am Customer Engagement Lead for Elysium. Elysium is hosting today's session and is also one of the GPDIS 2020 partners alongside Boeing, SimData, Northrop, Parker, and PDES Inc. I would like to start us off today with a big thank you to our sponsors, Anarch, Kubo Tech 3D, and Transmagic for sponsoring these sessions today. And before introducing today's speaker, I would like to touch on a little bit of the history and focus of GPDIS. The Global Product Data Interoperability Summit was formed in 2009. It was actually a consolidation of two conferences addressing integration technologies along with the non-proprietary exchange of data. GPDIS functions as a communications hub for industry principles to foster knowledge through the exchange of ideas, solutions, and methods. It is a place to build consensus on the data, tool, and process standards based on the experience of like-minded professionals. Every year, GPDIS encompasses a theme, and the 2020 theme this year is the Great Race of Digital Transformation, addressing the question, how is your model-based enterprise today? Many would claim that the digitization is complete. Enterprise has achieved model-based expectations. And indeed, there are petabytes of data, much captured in some form of a model. And supply chains are exchanging data at all levels, and our products are growing more intelligent every day. But is the digital transformation complete? Many would argue no. The digitization of existing business processes has certainly occurred, yet the true value of models and model-based thinking has not been fully realized. So together at GPDIS, we are exploring digital transformation and what it will take us to fully achieve it. And using the Great Race as a metaphor, we will explore the building blocks of digital transformation and how interoperability will enable the digital transformation journey for industry. And of course, as a reminder, we encourage everyone to mark your calendars for next year. GPDIS 2021 is currently scheduled for September 13th through the 17th, 2021. So today, as I had mentioned, Elysium has invited my good friend, Denise Fitzgerald, the co-leader of the Mechanical Engineering Group at MIT Lincoln Laboratory, to discuss Lincoln Laboratory's digital engineering transformation, including expectations, challenges, and solutions. And a little bit about Denise. With over 25 years of experience as a precision mechanical engineer, she co-leads the Mechanical Engineering Group at MIT Lincoln Laboratory, which develops complex hardware prototype systems critical to national security. She also leads the laboratory's Digital Engineering Transformation Initiative. In this role, she is evolving the engineering and operational capability of the laboratory through the use of analytical models to define and drive process while building a connected and efficient prototyping environment. She is definitely a champion for organizational change and modernization of engineering practice. Ms. Fitzgerald holds a BS in mechanical engineering from Worcester Polytechnic Institute and an MS in mechanical engineering from North Carolina State University. Without further ado, I introduce you to Denise. Denise, please take it away.
All right, thank you, Danielle. And let me just hide my video here. So I want to thank you. This is actually my first time presenting at a virtual conference, which means I can't see you all checking your phones, and I'm assuming you're all laughing at my jokes, so it's all good. So as Danielle mentioned, my background is that I'm a precision mechanical design engineer, and if you are a precision mechanical design engineer, you know that the last best day of your life is the day that you've finished your design and you've gone through this arduous process of thinking through all the eventualities, and you hit the button to go fabricate the parts. And it's the last best day of your life, because when the parts come back and you start to put them together, you realize that the reality of the physics and the tolerances and everything that you didn't actually consider are coming to light. And you have your moment of anger and sadness and panic, and you get over that very quickly, and then you decide how to solve the problem, and you make something great. So I mentioned this because I see digital transformation is no different than precision mechanical design engineering, in that you have a good plan and you go into it, and things don't always work the way you want them to. So you have your moment of sadness and anger and panic, and when you get past that moment, you decide how to change it. So I'm going to talk a little bit about what we've done and some of the challenges that we've seen. So quick note about where I work, if I can get my slides changed. There we go. Too much. So I work for MIT, which I'm sure you've all heard of. I don't work for the campus. So we're two parts. MIT is the great educational organization, but we're also in a totally separate facility 15 miles west of the campus. We're a federally funded research and development center. And what that means is we're a closed facility, and we do applied research for the U.S. Department of Defense primarily, also for other organizations within the U.S. government like NASA or NOAA or DOE. So our mission is to develop technology in support of national security. Now, if you don't know what an FFRDC is, it means we have a special advisory relationship directly with the government. So our job is to survey national security and find cracks in it that we think technology could fill. Now, we have a strong sense of non-competitiveness in that we don't go out and bid for grants or anything like that. The government funds us directly, and part of our job is to send that technology that we develop back to the government, back to industry. So they fund us at about $1.1 billion a year. We're split into different mission areas that look at different aspects of this national technology, or national security rather, and I work for the engineering department. So actually, we're a division of about 500 people, and what we do is we develop hardware prototypes. So the mission divisions develop the technology, and we then have a vertically integrated division who can do anything from systems design to CAD design to hardware development to assembly integration and test. And sometimes the purpose of this hardware development is to send something into space, and sometimes it's to run an experiment in the lab, and the deliverable is actually the result of that experiment. So this is our operational model. Like I described, we get input from national security, we develop ideas or awarded projects from the government, we execute those projects, and again, the result of those projects could be anything from the result of a study or the development of a technology or an algorithm to the development of hardware. And then our job is to send that back to the sponsors within the government or to industry, and then we want to reapply that research into further programs. So here's some of the examples. I'm not going to go into these in depth, but on the left you can see some of the technologies, and actually the slide is getting a little old now, so we've done quite a few more things, but we have a wafer fab, so we do a lot of advanced sensors, algorithm work, we do a lot with lasers. We would take that technology and my division would package it. So we've done anything from demonstrating two-way communication between a ground station on the Earth and a satellite orbiting the moon. So we do communication with lasers. We do desktop demonstrations on harmful aerosol detection. We've done very large radar dishes. So we do very, very wide range. We usually don't do more than 1 or 2 of something. So let's talk about the problem in general. So if you're in this community, you might be aware of the DoD's digital engineering strategy. And if you're not, I'd recommend that you look into it, because it's really where the DoD wants to go, and they're starting to develop the policies around this strategy. And basically, to summarize it, it says, you know, our adversaries are very agile and we're very bureaucratic. So it's getting to the point where the differentiator is the speed in which you can get technology out into the field. So in order to solve this problem, this digital engineering strategy was proposed, and it really breaks it down into 5 pieces. So one is to use computational models to express everything we do over the entire life cycle of any acquisition or any technology development, to have the systems that give us an authoritative source of truth of those models, to be able to incorporate new innovation into that technology stream, into that development, and then to have robust IT environments in which to run all of that. And of course, the big circle around all of those others is that we have to become a digitally mature workforce in order to be able to operate in this new digital environment. And that is the greatest challenge. So we know at Lincoln, in order to make the greatest impact, to give the greatest value back to the community, we need to become digitally mature, and we're not. So how do you become digitally mature, and how do you digitally transform? So it's really a twofold process. So first of all, if you're not digitally mature, it's quite possible that your processes are becoming complex. And they're becoming complex because the more people are in the chain, the more repetition has to happen of data being copied from one place to the other, of paper being passed around. So over time, your processes become very complex. At the same time, you might not have the capability to change that. So our approach is to bring the complexity down by bringing in better capability, and we'll meet in the middle. And that means bringing in better tools, but also maturing our workforce as well. So, we've broken this into 4 different aspects of what we do. So my initiative is the top tentacle of the squid, and my graphic artists loved that I called this a squid because we told them we didn't like pillar charts, so they made us a squid instead. So we're looking at the business tools that we use to run our business, the collaboration tools that engineers and business people use to communicate with each other, but then also how we approach engineering problems and how we develop that technology. If we bring all of those together, that becomes one digital enterprise transformation. So let's talk about digital engineering specifically. So we started this about 5 years ago, and this chart hasn't changed in 5 years other than I added our operational model to the left. But our goal is to enable an environment for efficient development of prototypes and dissemination of information. And to do that, we broke it down into the 3 main categories that we needed to focus on. We needed better environments for engineering collaboration. We needed to close that capability gap. We needed to take the administrative burden off of our engineers and researchers so that they could do what they're really there to do, which is to innovate. And then we know to be good partners to the community, we need to provide better and more complete and more informative digital product information back to the community. So that's great, that's the problem. That's the easy part, right? So now the solution. So in order to approach this digital transformation, I broke it down into 3 steps. So the first thing you have to do is you have to look at all work that you do, and you have to break it down and deconstruct it into data items. We'll talk a lot more, and I have an example right after this of what I mean by that. If you can break everything into its constituent parts, you can reassemble those parts in any way that you want into information. And then if you can use that information and you can get knowledge from that. You get organizational value from your transformation. So let me give you an example. So this is our typical way of working today. So we need to deconstruct this type of mechanism. So the systems engineer pictured in the middle here has to write an assembly procedure. They take requirements that may or may not be to the latest rev, a tool list that may or may not be complete, maybe some CAD models, and probably get some advice from various neighbors. So there's a lot of tribal knowledge going on. And they take pieces of information out of each of these sources, and they write their assembly procedure. And they make a copy of that procedure, and they go to execute it. So, of course, in the execution, it says record the voltage. And you handwrite the voltage in the procedure, and you have another systems engineer who then has to take that and put it into their V&V matrix to show that they've actually met the requirements. And of course, if you notice, they copied it wrong. So this happens all of the time. So this is the mode we work in now, and what we want to do is take a digital approach to that. So if we didn't view the requirements as the end product, but we said, let's break these requirements down into little constituent pieces, these little pieces of data. How could we reassemble them into information? So I could make an assembly procedure, and each of these blocks could be taken and assembled in a different way to have different meaning. And we get the point on the last one there. So, oops, sorry. And as I actually execute, I might create physical parts that represent those design parts. And I'd hit record, and I'd get the an actual measurement for what I was recording. But then I could take that information and I could construct it into an as-built structure. Or I could then take those requirements and connect them to the actual measurements that I took and prove that I've completed my V&V. So that's, again, the idea of using data as building blocks rather than just connecting different pieces of different files. It gets you to a much finer resolution, and we'll talk a little bit more about resolution as we go on. So what do you need to do that? What building blocks do you really need? Well, you need systems engineering. So, of course, I'm sure most of you are familiar with systems engineering. It's the modeling of systems, its behaviors, its interconnect, its performance, its requirements. So there is a push at the lab to move to SysML-based tools in order to digitally represent the system design. You'd need physical models because we deal with very large trade spaces. We're not given requirements, we're given a problem, and we have to go determine which way to approach the problem. So we've developed a homegrown solution called LEMIS, and what LEMIS does is it can connect different domain models in simulation, and it can do these very, very large trade studies to try to get you the best combination of results between, let's say, an optical system on an aircraft, with some thermal load on it. It can point you to the right place to start your design exploration. So we can take this and we can boil it down into a single set of metrics where we can do our trade space exploration and also our optimization of our systems. So then the third place you need to connect, and I should say there are more than just 3 models you need to connect, but I'm going to focus on these 3 to keep the presentation simpler. We do connect out to our business systems and other areas as well. But the third place you want to connect is actual hardware design and fabrication. So we've been doing digital design and fabrication using models for over a decade. The shift that we're making is to embed this PMI, this product manufacturing information, directly in the model so that the machine tools can start to read it, and it's taking some of the burden off of our inspectors and our machinists to consume that data. We're also reusing our models more and more to drive assembly and integration activities. And I didn't want to not mention PC boards because that is a little bit more of a digital tool, but we have, as I mentioned, we're vertically integrated, and we have advanced PCB fabrication facilities. But a lot of times what you get with PC boards is that you get a bill of materials and all of your components are on it with off-the-shelf component numbers. And then there's a note on it that says gold mitigated all parts. And what that means is if any of the leads have gold in them, you have to dip them. So that's how you mitigate them. So to transform that bill of materials of parts that you can't use into an MBOM that you can use and have the traceability of all of those processes that had to be performed to those parts is another step of digital transformation that was all done with spreadsheets for quite some time. So what you really want at the end of the day is you want to take all of those models, and of course the image of the gear is that if any one of them turns, they all turn, and there's an interconnect between all of them. You want to connect them all to each other. Now, if you think about it, the data coming out of an MBSE model is not compatible with a CAD model or these physical models. So you need something to translate between them, and we're using a PLM tool, Aris Innovator, to do that. So this will control the relationships between the models. We'll get into this quite a bit more. So the approach we've taken is, again, I'm sure most of you are familiar with the systems engineering V, but it just describes the various steps along the life cycle of a development of something, hardware most likely. We chose to start at the bottom, and we chose to start at the bottom with the detailed design because those were our processes that were most developed, and that's where the tools were most developed. So we've spent a few years working on that area. As we implement more, we're moving up the V. So the tools are now ready to start integrating systems engineering and then assembly integration and test activities. And then we'll move up further along the V until we cover the entire life cycle. Okay, so that was great. That was the last best day of my life. Now we went and implemented, and this was my image of interoperability, but the reality hit of some of the challenges and what happened. So we all know, as I'm speaking to you from my home, COVID happened, and we had at Lincoln this really unexpected and rapid shift to a digital workforce, and I'm sure you all had the same thing happen to you, so it's no different, but we went from less than 5% people working remotely to over 90% in about 5 days. So we had a lot of plans on how to slowly integrate and have an enterprise architecture, and that went out the window because we had to keep everyone working and operational, and we had to shift very rapidly, and the whole thing is awful. It's been a huge catalyst in the shift of our culture to a digital workforce. So I'll say that's the very, very small silver lining to COVID. But in doing that, we've had to look at all of these platforms that we've needed to bring in or needed to integrate in order to work. And I think some data has mentioned this before, and there's been plenty of reports that there's a trend in industry to move towards platforms. Everything is a platform with multiple tools. You can work all within one environment. Well, of course, you can't work within one environment. So there's this move towards these platforms, and they don't all work together. We have issues with security, so there's a strong desire to move to cloud-based platforms, especially in these current conditions. So we moved to MS365, but we're a government organization. We do government work, so we had to move to this GCC high cloud that doesn't have the connectivity to any of the applications that our good old-fashioned desktop tools did. We use a lot of Dassault products, but the new Dassault products work on a Dassault's cloud, and we're not allowed to use that for our security reasons. That's the French word for cloud, by the way. So there was a lot more opportunity for local customization that we found is a lot more challenging as we move out to these cloud-based platform solutions. And the other aspect of those cloud-based platforms are that work is changing, not just not just the IT aspects of it. So if you think about something like Office 365, this is a great advancement where we can work in a cloud-based collaborative environment where many people are modifying a document at once, but we haven't caught up with the CM processes that we've used for years and years, which says, I go and I check out and I change and I check in and the next person checks out and changes. So we've had to work with these, and I don't think we're completely caught up with this new mode of operation. And it's caused us to think about a lot of hybrid solutions in how we, and it's taken a lot more care in how we deal with environments like this. So what's the solution? I don't have the final solution. I can tell you what we're working on, and that was to bring in a good-sized enterprise architecture team to really look at everything we were doing in one scope. So rather than saying it's 4 legs of a squid, we're saying it's one enterprise, and all of these tools need to work together. And before we bring in new tools, we really have to understand the interoperability between them. There's a challenge there because we haven't had this for years, so we're balancing that enterprise-wide policy versus having local flexibility. So this is an ongoing effort, and it's a massive effort as well. But let's talk about digital engineering, because that's why we're here, to talk about interoperability. So I borrowed this slide with permission from my friends at ARIS because I liked how they depicted this problem. And the problem is basically, we talk about being model-based, but when you get down to it, you're not really talking about just one type of model, even as you trace it along the V. So when you get down to the hardware design, you're talking about a mechanical CAD model, perhaps an electronics ECAD model, software. None of those are compatible across the different domains. So how would you connect them? Well, MBSE is really the answer to connect them, because MBSE defines the behaviors and the interconnects between those different domains. So you really need that MBSE piece to really, at a very discrete level, connect those domains. So how do you do that? Again, this is an image of ARIS. So you need to find a common language in which to make those connections. So if you can imagine an MBSE model, and that has different blocks, you can take those blocks and represent them in a PLM as a PLM item. Well, PLM can do the same thing with CAD models and many other types of models. So now if we brought them all into the same environment with the same type of item, that we can define the relationships between them, now we can start to build out these connections. And this is great because you start to have traceability throughout all of your different domains and different models. But I'd argue that that's really not enough, and you really need to think about resolution. So when you think about the Lego blocks, what I really wanted to do was say that I had a requirement that was 24 volts, and I had a measurement that was 23.9 volts. I'd really like at the parameter level to be able to connect those two. I'd really like to know that the mass budget that I was defining in MBSE was transferred to my simulation model, so that I could use that to start running mass mockups and simulation to see that I was actually meeting the system demands, or if I needed to modify either one. So you really need to think at a much more discrete level than just models. We need to think about parameters and finding that common language between all of our models. And if you think about it, again, going back to my Lego example, a lot of times documents were that kind of connective tissue between our models, and we need to be thinking about how we can tie those parameters into something like a document. So I'll give you another example. So if I have this common language, this PLM item, this container, I might be able to link it to a CAD model, and maybe my CAD model has all that great PMI that the machines can read, and maybe it has some graphic PMI, because in many CAD systems, you display your notes as just text kind of hanging out in the model, and maybe you throw that on a drawing. I know we're going towards MVD, but we still use drawings, even though we don't actually define anything on the drawing. So at times. So you could probably take that graphic PMI and you can pull it into the PLM, but that doesn't really give you a great resolution. If instead you moved all of that graphic PMI information, a lot of times that's things like material and finish and manufacturing instructions. If you move that up to the PLM and you started to classify it and you started to turn those items into parameters, there's a lot you could do with it. So if you think about it, and then if you had a tool where you could take the little parameters that you wanted and package them together, you could create a technical data package for fabrication by knowing the pieces that the manufacturing folks need. Or you could have it from the same data set, a TDP that inspection needs. Or you could start to link your requirements where your requirement says that I can't use any organic materials, and you say, okay, that's not organic, so I'm good. And then you can start to build a knowledge base around that because you have a fine enough resolution that you can look for issues. So if my knowledge base says that you can't anodize steel, I can see that I have aluminum and it's black anodized, and that's good. If I had steel, maybe it could warn me before I ever tried to make those parts. So, and thank you, Elysium. It's often hard for me to get real images released, so I've borrowed from many people. So thank you, Elysium, for letting me borrow this one. But this is an example of one of these generated PDFs, one of these technical data packages, and the idea being that you could take some part data information images, and on the second page, you could take that semantic PMI and have it in a rotating PDF window, and then you could extract all of those notes and other information that you need to fabricate from the PLM and display it on a third page. And the best thing about Elysium's technical data packages that we've totally stolen is that they actually have a button that says help, and it tells you how to use the data package. And we had to cancel it. We almost had to have a seminar for our supply chain to explain to them how to use, I know we don't like to call them 3D PDFs, but 3D PDFs. And we said, well, this just solved our problem. So it's a great tip. So our current model-based capability, as far as mechanical, we can create and fully annotate models. We have a configuration management process. In our PLM infrastructure, that metadata that we take off the model that's stored with that PLM item gets passed to our ERP system where it creates materials. It also creates orders. We can take that model and use it in CAM for programming. We can also use it for inspection, and then we can pass the data back into the system, and we create that digital thread. And we're currently working on those Lego assembly procedures that I used as an example in the front. So let's concentrate on the left side of this, since that's what's done right now. So the problem kind of came up in the model-based community. We have MB, lots of things. We don't talk about MBH, which is model-based hope. And the model-based hope is that you define and design, and you control, and then you use the same model and you fabricate, and use the same model and you verify. That doesn't quite work, because what really happens is you design and then you defeature that model to simulate it, and it's usually two different people doing that work, and somehow you get the feedback from the simulation folks, and you converge on a model, and you finish your definition, and you publish it, and you configuration manage it. But then it goes off into two parallel paths, and the fabrication folks often have to put other features on the model in order to do their work, and so do the inspection folks, and a lot of times they're not doing this in parallel. A lot of times they're not doing this in series, they're doing it in parallel, so they can't make use of the same models. So at the end of the day, the model that you controlled is different from the model that you actually used. So traditional CM doesn't really support this because it says, well, I've got to do a bunch of approvals. I have to have 12 engineers approve any change. Well, they didn't really change the model. They added some features that they needed, but it's hard to roll those back into our traditional process. So what we've been looking at is, can you, again, break that down, break that resolution of the model down into something that you can validate whether it had an effective form, fit, and function. And if you could use a tool like Elysium has where you can compare two versions of a model, you can start to look at what the differences were. So if you can show that there were no differences to geometry or no differences to your PMI, then you can automatically roll in changes back into the model without having to bear the burden of that approval-based CM process. And then not only does that comparison and validation become the record of change, it also becomes the decider of change. The last thing I wanted to talk about is cultural interoperability, because that is the biggest problem. Is your culture ready for the advanced tools? So I'm not going to go through all of these items, but this is my take on Lincoln's culture. So we do a lot of programs. Everyone's really busy. We have a high workload, not a high turnover, which means we're a little old. So people have been sometimes stay at Lincoln for their entire career, so they don't really see how other organizations work. And we come from a very, very much paper-based mode. So you kind of have to think about how people think. We have a relatively flat organization, so you got the director's office, the division office, and the group offices. And they're the leadership of the laboratory. They're the strategic thinkers, and they're totally driven by opportunity. So when I talk to them about this, they say, yeah, this is the future. This is what our sponsors want. We've got to do this. Go do it. But then you get down to the people who are actually executing the programs, and they're very tactical minded, and they're driven by risk. So they're saying, but this sounds different, and I really only care about my program executing on time, so I really don't want to do this. And then you get down to the operational thinkers, and they're totally driven by process. They don't really think so much about the big picture, and they just want to know what to do. Don't care so much about how they need to do it, but a change to what they do is very uncomfortable. So I thought in the last few slides, we'd have a little fun with some cartoons, and let me tell you, these cartoons were toned down a little from me venting on a slide, but I'm the person on the left, and the person I'm talking to is on the right. So when you approach the strategic thinkers, and the little blue box tells you everything you read in the books that you should do for organizational change management. But, you try to get organizational buy-in. Everyone agrees it sounds great. And then you talk about it. You kind of get a blank look, but they still seem with you. And then you ask them, to help you. And almost all the time they say dashboards. It's across the board. So, you realize the digital maturity is going to take a little while, and a lot of these concepts really takes a while to internalize. So bringing up very simple concepts like my Lego blocks is a lot better way to explain it to people than explaining the whole digital transformation at times. So let's think about the tactical thinkers then. So everyone wants dashboards, of course, and then you ask them every time what's on the dashboard, and they just say, well, everything to make my life easier, but they don't really think about what that means. And then you try to gather user stories, and you get, this is a true story based on a true story. So, and it says, someone prints out the file, gives me 3 copies, I throw out 2, then I scan the 3rd one. I've always gotten 3. I've always done it this way. So most of the time I don't hear, I would like to do it this way. Most of the time I hear, well, this is how I do it, and it's a little, doesn't make sense, but this is how I do it. So you try to deconstruct that, but then it starts to look a little different. So we try to do this in steps. We do proof of concepts, we do pilots, and you realize these people are really, really busy, and when they have to stop and think and look at it because it's different. And even though you've explained to them it's going to be different, they don't actually conceptualize how different it is. So when you explain, well, but there's a benefit to this, and then I've actually sat there at one point talking to someone for 2 hours explaining how this would save them time, and when they finally hit the 3 buttons, they said, oh yeah, it does. But it took 2 hours of convincing them to hit 3 buttons. So, you know, think about the drivers for your organization. For us, it's risk. So, you know, try to make the reward to that risk better, and try to find the people who don't see this as a risk and are willing to take it on and want to share the knowledge. And then last, the operational guys, you know, they really need a process to follow, and we've tried Agile, and of course you can't just let them go and try things on their own. You really need to explain the process and check in constantly and sit with them and explain what's going to happen and paint them a picture, because as my cartoon says, they just keep pushing the button that you told them isn't going to work because you were trying to get an idea if they like the interface. So, you know, trying to get participation, and you really need to sit with people, and you really need to get people involved who will very, very much be hands-on with new users, because a lot of these concepts are very new, and not everyone really understands kind of at a high level where you're going. And user feedback, a lot of times we get user feedback, it just says it didn't work, this button failed, and they don't tell you how it should work or what should happen. So really having observers who understand what you're doing and to collect that data is really important. And then you go live and they say, I wish you'd asked me for feedback, even though, you know, for 2 years you had been. That's usually me. So so what do we do about this? So we actually reorganized our whole structure. So we have a core team that is there to do the development on this digital engineering connectivity piece. And then we've split our division up, and we kind of fundamentally split our division. So we're split into groups by disciplines: mechanical engineering, systems engineering, optical engineering, 8 different groups. What we did instead was we said, well, that's never going to work because no one can think outside of their domain. So we're going to split the division up into the work that we do. So mechanical realization, for example, is a stream of design, simulation, machining, and inspection. So the person who's in charge of that entire value stream has to look at the flow of data throughout the entire value stream, not just the group that they belong to. So it's making people think about what happens to the data after it leaves their desk. And it's trying to gain that understanding, that greater understanding across the division. And on the other side of the matrix, we have the people who are actually responsible for implementing that in the tool, or you know, I implemented. They have to be responsible for it once it's implemented. So we have a group that's looking at what and why, and a group of who and how in their matrix, so they have to work with each other. So at the end of the day, this is my final thoughts on just about anything. So whether it's precision mechanical design engineering, or digital transformation, or PLM implementation, you have to know the problem and that you're trying to solve. And our problem statement never changed, and our goals haven't changed. And that makes me feel that we're on the right path. The design solution changes, and it should evolve as you learn and as your approach to things you know, evolves over time as you understand the problem. And then, you know, the reality in the solution is basically that, well, not everyone shares your vision or understands your vision, and that could be externally. It could be Microsoft doesn't really care so much what Lincoln Laboratory is thinking, but and you know, the inspector doesn't care so much what Lincoln Laboratory is thinking, but at the end of the day, that's not going to change, so they just deal with that. So what has worked for us is to look for that common language and that synergy between all of these domains to find that glue that ties them together. So that's all that I have for today. Thank you for watching. I'm going to hand it back over to Danielle for an announcement.
Yes, thank you so much, Denise. We really appreciate your time. And we do have about a little over 10 minutes for any questions for Denise. Please feel free to submit those into the chat. Yes, as we get to those, one announcement we do have is please join us for the next GPDIS session on Tuesday, October 27th, where Jack Harris, CEO and General Manager of PDES, will be talking about standards impacting business performance. And if anybody needs to get a hold of the recording or presentation from today's presentation, or even any previous sessions that you might have missed, those will all be available on the GPDIS website, gpds.online.com/event history. So with that, we have a little bit of time if anyone has any questions. So please submit those. And I actually have one, Denise. First of all, I absolutely appreciate and love the Legos for the building blocks. I think it does make it very easy to break down. And model-based hope gave me a great little laugh as well.
See, that's what I thought. Everyone out there was laughing.
Exactly. I can attest to that. So one question that I have, because I've heard you talk about this in some examples. You do spend a bit of time on culture, because it really comes down to, you can find the best solutions in the world, but if people won't use them, it doesn't matter. So do you have any specific examples of ways that you found to kind of implement change for people that either were reluctant or didn't even realize it was happening? Do you have any examples that you could share for that kind of change?
Sure. Yeah, there's a few things. So, I mean, a lot of times you have to break people down a little bit. We like to ask the 5 whys. So when you get a user story like the one I explained about, you know, getting 3 prints and throwing them all out and then just scanning them back, even though they came from a digital system, we say, well, why do you need that? Well, I've always gotten it, but why do you need it? Well, I don't really need it, but I put it in the file. Well, why do you need it in a file cabinet if it's already in the digital system? Well, and then you get, I guess I don't need it. So sometimes you have to break down those preconceptions. So we do that. Sometimes people kind of get it right away, and other times people are adamant, and you know, and sometimes there are real use cases too, and that it's helpful to try to get the real story, because sometimes it's really hard to extract the need versus how you do things. So that's one thing. You know, and the other thing, if you've ever heard me at other conferences, sometimes we just trick them. So I mentioned very briefly that we still use 2D drawings. So we do, and you know, our long-term goal is to go fully TDP, but we found that some people are uncomfortable with the 3D, again, 3D PDF, the you know, spinning model on a PDF, and they're very used to seeing those multiple views on one page. So so we've slowly removed all of the content off of the drawings, and we put them in the models in a way that is a little bit transparent to people viewing the drawings. It's really no different to the people creating the models, because we give them interfaces. So we've kind of replaced, you know, replaced their work very gradually, and you know, we're almost all the way there. It'd be very simple to just do that final switch. And we've even been talking about, well, maybe our TDPs are just, you know, a view with a model and a view with a flat drawing. And for the users like the guys at the front of the house for the little mom and pop machine shop that just wants to take notes on a drawing, maybe that's more useful than you know, fighting it right now. and we still have the great 3D content as well, and all of the benefit, because once you get to the guy doing CAM or the guy doing the CMM, they like the 3D content.
Got it. Great. Thank you. And one kind of follow-up, I know that a lot of the culture is it's a long-term plan, but you did actually mention, of course, as we've all experienced with COVID, and kind of it became the catalyst for you. What were those, first few days really like? What were the things that enabled you to make that switch? Like you said, less than 5% over to the over 90% remote. What were some of the things that maybe any kind of company could adapt or do to really make that switch? Because I know you've talked about it you always talked about it's not possible, and then all of a sudden we made it possible. So what are some of those tips and tricks maybe for making it possible?
Yeah, besides worldwide pandemic.
Yeah.
Yeah, hopefully we don't have another one of those. I think, it's necessity. Lincoln is a very conservative culture, so our security would prefer to say no. Where it got to the point where we said, is it really no? Or, can we do this? And they said, well, it really wasn't a no, we just thought it was safer not to. So, when we really had the true business needs sitting in front of them, they said, okay, we have to change. The cultural change, it took a bit because not everyone had laptops and not everyone has cameras, even still, these are all back ordered, but it was getting like I manage a large group of designers, and they weren't all comfortable with the digital tools, so it was, okay, well, we're going to use them, and whenever you see me in a meeting, I'm going to have my camera on. And it's taken, whatever, it's 3, 4, 5 months now, you see more and more in meetings, engineers have their cameras on. People are talking because they're all complaining, well, we don't see anyone face to face. Turn your camera on. So, it's whenever you get a chance, when you're in a meeting with someone, demonstrate it. So, we use Zoom primarily. So, saying, hey, let's whiteboard this, or hey, can you bring that model up that you have a question about, and I'll start annotating it. And they're like, well, you can do that? So once they see it, then they start doing it. So sometimes it's just, again, the necessity is right in front of you. Show them a different way of doing it.
Yep, show by example.
Right.
Pretty straightforward way of doing it. Well, again, I want to thank you, Denise, so much for coming to speak for GPIS today. I absolutely found it fantastic, and I definitely learned a lot. And I've been watching you and working with you for so long, and I'm still learning more from you. So thank you so much for taking the time. And everyone who joined us today, thank you so much. Again, if you need the recordings or the presentations, or if you missed any or might miss some in the future, please don't hesitate to reach out to the GPIS website and find those recordings. And we hope to see everyone again on our next session on Tuesday, October 27th. Thank you, everyone, for your time today.
Wait, Danielle.
Yeah.
We had some questions sent privately, and so if you don't mind, we have a couple more minutes.
Oh, absolutely.
Denise doesn't mind?
I don't mind.
Let's see, great presentation. Have you approached the business case selling the digital transformation and associated digital enterprise to the organization problem? It's a long journey, and the business wants a return on savings quickly. Back to your risk avoidance comments.
Yeah, it really is. So, our programs are anywhere from 3 months to 2 to 3 years. A few programs will be longer term. So, the real short-term programs, they are really concerned that any bump in the road, the day of training is on their critical path. So it's hard to get to those programs to switch over. So we're taking more of an approach of evolution, where we're saying, okay, you're in the middle of a program, you keep going the way you're doing it. The next program you're on, the next new program starts with the new digital tools. So it is taking longer, but we're allowing a more natural evolution. We're looking at, are there parts of the life cycle? Like we don't have to have the entire life cycle in the PLM system. We could start with assembly. We can get the BOMs in, the information we need in. Would it make sense to start there and not have design? So we're considering, could we get a little more adoption sooner by doing things like that? But for right now, we're just taking a slower evolution, and in ways it's good because when people find issues, we're able to fix them, and we're not having to, we don't have quite the same pressure for a huge community using this tool.
Great. Thank you. The next question is, can you review again the difference between MBSE and digital engineering, understanding both their strategies?
Sure. So, yeah, this is the fun of being in the model-based world, because the definitions are overlapping and evolving over time. So MBSE is model-based systems engineering. And it is specific to a set of tools that define your system. So it breaks down a system into constituent blocks and behaviors, activity diagrams, requirements. So all of those are linked, and if anyone changes, you can see how they filter through the system. So to me, what we consider digital engineering is really the entire life cycle. So MBSE tools don't really address hardware models or those physical models. So for me, digital engineering encompasses all the entire life cycle of whatever your life cycle is: product development, acquisition. You'll hear it in the DoD environment as well. So, it's any model, it's any analytical model. It could be a data model in your ERP system. It could be, any sort of representation of data within that life cycle in a computational way.
Great, thank you. I think we have one more question. There's one comment. It doesn't really look like a question, but I thought you would want to hear it. Your slide 45, all the 4 panels were good, but that was priceless. So they obviously like slide 45.
Oh, well, let's see what's slide 45.
While you're going there. Yeah, that's good. And the last question, what is the link between PMI and the digital requirements that may reside in a dedicated requirements management system? It's not allocation, traceability, synchronization, validation.
Sure. So, yeah, it depends what your requirements are, of course, and that's why understanding your resolution is important. So, so let me think of an example. If you were doing let's say you're doing a space program, and there's requirements for having low outgassing materials. So, if you could break down that that hardware model into your material, each material was a parameter, you could then query, are these organic materials or these low outgassing materials against that requirement? That would be an example. Mass would be an example. If you have a mass budget, are you pulling out the mass from your models? Now maybe you're comparing your assumed mass from your CAD model to your actual mass to your budgeted mass, but that's another way you could think about tying in. We do all sorts of budgeting like that, so you could tie in your requirements to the PMI. Now, again, the semantic PMI, maybe there's not quite so much of the need. If you get down to, I don't think I've really seen a flatness or a tolerance tied into requirements so much. Maybe there would be. But, there are other items in the system too. So, for example, maybe do an inspection report of some sort, and you want to say that, well, this particular piece of semantic PMI failed, and now you start to notice organizationally that anytime we have a feature like this with this level of tolerance, it fails. So let's look at our our manufacturing processes. Maybe we can do better. Or maybe we just can't do that, and we feed that back to the engineering community and say, hey guys, you're being a little harsh here, or you might want to think about not having such tight tolerances. So
okay, great.
Hopefully that answers. Yeah, I mean, there's when you start thinking about the Lego blocks, I use requirements as an example because I think a lot of people can latch onto it, but there are all sorts of connections. If you really start to think about the relationships between every piece of the work that you do, kind of down at that Lego block level, you'll find a lot, and it was a lot more than I expected.
Great, thank you so much, Denise.
We're engineers. We like building with Legos.
We actually had one more question come into the Q&A, I think. Lily, I'm not sure if you can see that. So I do have one more if we have another minute.
Sure.
Yes, sure.
So we had a question of, did you spend any time reviewing ROI, or was that not necessary because management was already on board?
I did. And I did two things at the beginning. I did many things at the beginning to study the problem. One thing I did was we had a workshop. We collected pain points, and we mapped out our end-to-end process, and then we collected where the issues were. We didn't really measure them so much, but I do measure, did we actually is the solution that's in place now addressing the pain? So that's one thing. So that's just a pure. I've addressed 285 of my 325 pain points that I collected 3 years ago. But the other thing, that the ROI that I did, so we realized that a lot of this transformation will help engineers, and that second item on my list of goals, which was take the administrative burden off the engineering community. And we realized that a lot of their day is spent finding information or not finding information. So we did a study, and it was small. We took 5 to 8 people, and there were people who were new to Lincoln. There were people who had been here for quite some time. We looked at which programs they were working on, and we tailored the questions. They were the same questions, but we tailored them to their program. The questions were, you just ordered this part, who's making it and when is it coming in? Can you find a subject matter expert on this? This poster is in our lobby. What is it? Can you find out one piece of information? And that was kind of the vein of the information. So, and we gave them a timer, and we said, please track how much time you're spending looking for the answers, and please tell me how long it takes you to get the answer. So what we found was no one could, I think we had one person finish. No one can find the answers to very simple questions. A lot of the answers were wrong, and it took about 20 people to find the answers to these 5 questions each, and they weren't the same people. So when you added up the time, and these are questions people ask all day long, it was millions and millions of, it was a ridiculous number of hours and dollars when you consider a division of 500 people all kind of asking the same questions. So that was the ROI that we did. So we haven't redone that, but I can show you, I can get to the same answers in about 2 minutes in the PLM system now. So we're well on the way of getting there.
Great, thank you so much again, Denise. So just to do a double check, we do have one final question, actually. Everyone's taken advantage of a little extra time. Did you utilize AP 243 standard for your TDP technical data package?
So at first we did, and I haven't queried the industry lately, but no one could read it when it first came out. So we were we were excited to use this because we said, oh, you know, this will be how our, so if you don't know what AP242 is, that semantic PMI that machine tools can read is embedded with the model. So if you just get a step model today of one of the other standards, you just get the geometry. This gets you the geometry and the PMI. So when we tried it a few years ago, we couldn't find too many machine tools who could actually consume it. So we went away from it. You know, it's something I need to revisit as the CAM and CMM companies, you know, they come out with new versions of their software. So I forget which one I forget if we're using 214 or what's the other one? Let's get the numbers backwards. 233. So anyway, we're using one of the just geometry standards for now.
All right, I did a final check. Looks like that was the last question. So thank you again, Denise, and thank you everyone for joining us today.